Hello and welcome back to Introduction to Number Theory. In this video, we will discuss the application of prime factorization theorem to a specific case. Consider such task. Find the minimal possible positive integer n such that n divided by 2 is a perfect square, which means the square of an integer, x should be an integer. N divided by 3 is a perfect cube, which means third power of an integer, and n divided by 5 is a perfect fifth power of an integer. Well, there are infinitely many such positive integers, and we need to find the least one, but actually we will find them all. And first of all, we begin by considering the prime factorization of n. Well, we see that n is divisible by 2, and 2 is a prime number, so one of the prime factors of n should be equal to 2, but we do not know the power of this prime factor, so write alpha. Then we see that n should be divisible by 3, so write 3 to the power beta. And we also see that n should be divisible by 5, so write 5 to the power gamma. But this is not all, because n could have other prime factors, and we take all other prime factors, including their powers, and collect just in one positive integer m. m is not divisible by 2, 3, and 5, but it can be divisible by other prime numbers. Now, how do we fulfill this condition? How does this condition depend on these powers alpha, beta, and gamma? Well, n divided by 2 is equal to 2 to the power alpha minus 1, 3 to the power beta, 5 to the power gamma, and m. And in order for a positive integer represented in prime factorization form, in order for an integer to be a perfect square, all of its powers, all of the powers of prime factors should be even. And this is the direct consequence of the prime factorization theorem, namely the uniqueness of the prime factorization. So alpha minus 1 should be even, beta should be even, and gamma should be even. Let's just memorize this and continue to n over 3. n over 3 is equal to 2 to the power alpha multiplied by 3 to the power beta minus 1. It's really similar case. And now, in order for a positive integer to be a perfect cube, all of these powers must be divisible by 3. Well, this is necessary condition, but it's not sufficient because we don't know what's happening inside m. Well, m should be a perfect square itself, and here m should be a perfect cube itself. However, we obtain the following conditions on alpha, beta, and gamma. Alpha should be divisible by 3, beta minus 1 should be divisible by 3, and gamma should be divisible by 3. Moving on to the third condition, n over 5, n divided by 5 should be a perfect fifth power of an integer. It's equal to 2 to the power alpha, 3 to the power beta, 5 to the power gamma minus 1, and m. So, just as in previous cases, alpha must be divisible by 5, beta must be divisible by 5, and gamma minus 1 must be divisible by 5. So now we need to find the smallest possible values of alpha, beta, and gamma, and the smallest possible value of m. Well, the smallest possible value of m is obviously 1. M is greater or equal to 1, and eventually, of course, we will take 1 for m just to obtain the smallest possible n. As for alpha, for instance, alpha minus 1 is divided by 2, is divisible by 2, alpha is divisible by 3, and alpha is divisible by 5. Even here, we can apply the uniqueness of factorization, because if alpha is divisible by 5 and by 3, this means that alpha is divisible by 15. Since alpha is divisible by 15, it could be 15, 30, 45, but from here we know that alpha is odd, so the smallest possible value of alpha is 15. Sorry. The other way. Okay. As for beta, we see that beta is even and is divisible by 5. This means that it is divisible by 10. But beta minus 1 must be divisible by 3. Well, since it's divisible by 10, then it could be 10, 20, 30, and so on. But 10 itself satisfies this condition. Therefore, beta is greater or equal than 10. And finally, gamma is divisible by 2, divisible by 3, so it's divisible by 6. And 6 minus 1 is divisible by 5. So gamma is greater or equal to 6. Finally, we see that the smallest possible value of n smallest is equal to 2 to the power 15 multiplied by 3 to the power 10 multiplied by 5 to the power 6 and multiplied by 1, and it's a really huge number. There was no chance we could find this number just by checking several numbers whether they satisfy the condition or not. This is the smallest value of n, and well, in general case, n will be equal. Well, instead of 15, we can write any power which is divisible by 15 and odd. Okay, we can write it as 15 multiplied by 2k minus 1. And we need to raise 3 to any power such that it's divisible by 10 and yet gives remainder 1 modulo 3, which makes it, well, 10, since it's divisible by 10. 10 multiplied by, well, 10 itself gives remainder 1 when divided by 3. So 3L plus 1 should do it. And finally, the power of prime number 5, well, it should be divisible by 6. Gamma should be divisible by 6. So it's 6 times, and it should give remainder 1 when divided by 5, which means that we should multiply it by, well, something that gives remainder 1 when divided by 5. So 5, what letters have left? K, L, M, N, O, P, Q, are s. We'll use s. 5s plus 1. And this will provide that gamma gives remainder 1 when divided by 5. And instead of m, we could use any number, but only if this number was perfect square, perfect cube, and perfect fifth power. So this means that it should be perfect 5 times 3 times 2 30th power of an integer. So this is the general expression for n, and it's quite frightening, so I think it's time to finish this part. See you.